Welcome back to another explainer. Today, our goal is super specific and honestly highly practical. We're going to take a notoriously abstract, kind of intimidating coding concept and transform it into a simple, repeatable mental model that you can use over and over again.
Backtracking feels like magic until you see the template. After that, it's just code. If you've ever stared blankly at a complex algorithmic solution, and let's be real, we all have, you know exactly what this means. It seems like the computer is just magically, inexplicably finding the right answer. But I promise you, while backtracking might seem intimidating right now, it relies entirely on a really simple, deeply predictable structure.
Here's our quick roadmap for this explainer. 1. The magic of backtracking. 2. A real-life maze question. 3. The step-by-step template. 4. Examples using subsets and permutations. 5. The power of pruning. And finally 6. Mastering the core patterns.
All right, let's jump straight into section 1, the magic of backtracking, unmasking the algorithm.
Okay, let's really dive into this. So backtracking is essentially a brute force technique. It tries all possibilities and undoes the choices that just don't lead to a solution. At its heart, yeah, this is just an exhaustive search. It's brute force, meaning it's perfectly willing to check literally every single possible avenue. But here is the absolute genius part. It's smart enough to reverse its mistakes the very moment it realizes it's on the wrong path.
Which brings us to section 2, a real-life maze question, escaping the abstract.
To really get this, imagine you're trying to find your way out of a massive physical maze. You're walking along, making your turns, and then, boom, you hit a dead end. So what exactly happens next? I mean, you don't just magically teleport back to the starting line, right? Think about what you actually physically do in that moment to solve the problem.
Let's literally walk through those sequential steps. Step 1, you take a path. Step 2, you hit a wall. That's your dead end. Step 3, you physically walk backward, completely undoing your last few steps to return to that previous intersection. And then step 4, you try a totally new path. This physical, everyday, real-life sequence, it perfectly, beautifully mirrors the computer's logic.
So what is the crucial difference here? Well, standard recursion is just calling a function within itself. But backtracking? That's recursion plus that critical undo step we just experienced in our physical maze. Literally, just walking backward from the dead end is the sole difference between the two. That's the whole shebang.
Moving on to section 3, the step-by-step template, your master key.
All right, this right here is your literal step-by-step code blueprint. Step 1 is the base case. Basically, did you find the exit? If yes, save your current state to the result and return. Step 2, loop through your available choices. Step 3, make a choice and recurse. You walk down the path. And step 4, the absolute magic ingredient, undo the choice. If you hit a dead end, think back to our physical maze. What do? You physically walk backward before trying a new path. That is step 4 in a nutshell.
Let's put this into practice in section 4. Examples, subsets, and permutations.
Let's see how this exact same template effortlessly solves two completely different problems. Think of a real-life scenario, like packing a backpack for a camping trip. For subsets, your choice loop is just a simple question. Do I pack the flashlight? Yes or no. Include or exclude. And the undo action, you just unpack it. Easy. For permutations, it's more like figuring out the perfect order to run a list of errands in town. You look at your unvisited stores, visit one, and then when you're backing up your schedule to find a better route, you unmark it. It's incredible because the exact same 4 steps apply every single time.
Next up, section 5, the power of pruning, optimizing the brute force.
So, pruning. Pruning is simply adding specific conditions to skip branches early, which reduces your execution time dramatically. Honestly, think of it not as a completely new algorithm, but as a superpower you just bolt onto your template. Imagine being back in our physical maze, looking down a super long corridor and knowing instantly, without a doubt, that it leads to a dead end without having to walk all the way down it. You basically just prune that path right out of your mind.
Let's actually apply this. Say you're working on a problem like combination sum. If your remaining target dips below 0, why keep calculating? You immediately know there's no way a valid answer lies ahead, so you just stop. You don't recurse any further. That really simple mathematical check, that's your set of pruning shears. Cutting off impossible paths before you waste precious computational time walking down them. It's a total game changer.
Finally, we arrive at section 6, mastering the core patterns.
Here are your absolute keys to the kingdom. 1. Subsets. 2. Permutations. 3. Combinations. And 4. N-queens. I really want to emphasize this. Mastering these specific big 4 problems means you've functionally covered pretty much every single backtracking pattern out there. Once you can consistently apply our template to these 4, you literally hold the master key.
So, I'm going to leave you with this final thought. Subsets, permutations, combinations, or n-queens. Which pattern are you going to conquer first, using your new template? The magic has officially been unmasked, the step-by-step logic is right there in your hands, and you know exactly how to back out of the maze. Dive in, start coding, and see the power of backtracking for yourself. Until next time, stay focused and keep on learning.